Hi dear students, welcome to my video class. In this video, I will introduce you a small topics to determine order of reactions. Suppose there will be a question, how to determine order of the reactions. There are four methods to determine order of the reactions. Order of a reaction is the experimental quantity. Therefore, whatever the method you use, the data of the method, the data to determine the order of reaction should be obtained through the experiments. That means you cannot determine order like determining molecularity just looking at the balanced equation. The coefficients of balanced equation tells you the molecularity of the reaction, but not the order of the reaction. Therefore, there should be very specific methods to determine order of the reactions. Different scientists like Van Hoff, Oswald, etc. introduced different methods. These methods are suitable to different types of reactions. We can discuss one by one. There are differential rate expression method, integral rate expression method, half-life method, isolation method. We can go to first differential rate expression method. Differential rate expression. This is a one method. In this method, rate of reaction is used to determine order. Consider rate law expression of a general reaction. That is, R is equal to K into concentration raised to N. K is rate constant, C concentration of reactant, N is the order of the reaction. One is, if you take ln R, you will get N ln C plus ln K. You will get an equation like this, ln K. This is ln R. Therefore, if you draw the graph of ln R, ln C, you will get a graph like this. A graph like this with the slope n. That slope of this graph is order of that reaction. Fine. In another way, consider this reaction with the two different concentrations. Therefore, ln R1, because when concentration increases, rate will increase, rate will change. Concentration changes, rate will change. Therefore, you will get Kc raised to N. Same reaction with the concentration C2, order N, K is equal to ln R2. Okay? Therefore, you make make it equation number 1, equation number 2. Therefore, 1 by 2, 1 upon 2, that is ln R1 upon ln R2 is equal to C1 by C upon C2 all raised to n. Okay. Now you know what happens. I'm sorry, really sorry. Something wrong. Here there is no ln, something wrong. Please. Suppose R1 is equal to, really sorry, R1 is equal to K into C1 raised to n R2. Now apply the ln. Ln R1 by ln R2 is equal to n into ln C1 by C2. You bring this here. Therefore, ln R1 by R2 all divided by ln C1 upon C2 is equal to n. This is also order. Therefore, through differential expression method, this you will get order in two ways, either in graphical way or in this way. Fine. Now we can go to the integral expression method. Integral rate expression method. Integral rate expression method. Here are also two ways. First is this method uses integral rate expression. Integral rate expression. Differential method uses rate expression. Here integral rate expression. Again it has first graphical method. Graphical method. Here also graphical method can be used. Each integral rate expression has characteristic graph. Therefore, just seeing the graph will give the order of reaction. For example, zero order. You know, zero order graph is like this. T concentration. Okay. First order graph. But ln A. Therefore, y-axis is concentration, x-axis is T. You have a negative slope graph like this. This is zero order. Y-axis is ln A. X-axis is T. You have a graph with a negative slope like this. It is a first order graph. Second order is a different graph. I suggest you to go to revise graphical expression of various order which have been discussed in previous videos. Okay. Second is analytical method. B. Integral rate expression. Second is analytical method. In this method, assume certain order for the reaction. We are assuming, it's a trial and error method. We are assuming certain order, suppose zero order. We assume that is zero order for certain reaction, comma, and calculate rate constant of the reaction. We have done a problem with this method. Suppose you have given a data and you have been asked what is the order of that reaction. The trick is, the method is, you assume it is a zero order reaction. You first assume that. Then take the zero order equation, that is A0 minus A is equal to Kd. Then you apply the data here, initial concentration and concentration at different times, and get the value of K. That is, calculate the rate constant of the reaction. If the value of K is constant, the assumed order is correct. Okay, I will tell you, suppose you are given initial concentration 1 molar, A 0.5, 0.25, 0.1 at 10 minutes, 20 minutes, 30 minutes. Now you have been asked, from initial concentration 1 molar, the concentration of reactant has been changed to 0.5 molar, 0.25 molar, 0.05 molar at different time intervals. Okay, then what is the order of that reaction? Therefore, first we will assume it's a zero order reaction. Therefore, we will take first this data, that is A 1.5 is equal to 10 into K. Therefore, K is equal to 0.5 divided by 10. Now again we use this data, initial concentration 1, 0.75 is equal to, time is 20 into K. Therefore, K is equal to 0.25 by 20. This K and this K are different. Therefore, it is not a zero order. Now you go to first order equation. What is the first order equation? K is equal to 2.303 log A0 by A by T. And calculate K for different values. If it is constant, that will be a first order. This is an analytical method using integrated rate expression. Dear students, the third is half-life method. Half-life method. Let me check the video. Yes. You know, half-life is inversely proportional to concentration. Suppose T of at concentration raised to n minus 1, I'm really sorry, concentration raised to n minus 1 at two different concentrations. Therefore, T of 1 directly proportional to A1, concentration 1 raised to minus 1, T of 2 directly proportional to A2 raised to n minus 1. Okay. Suppose it is equation number 1, 2. Therefore, T of 1 all divided by T of 2 is equal to A2 all raised to n minus 1 divided by, we can make this a common, A2 by A1 all raised to n minus 1, all raised to n minus 1. Okay. In the first we have a differential rate expression R1 by R2, like that. Now apply ln T1 by 2 1 all upon T1 by 2, 2 is equal to n minus 1 ln A2 by A1. A2 by A1. Okay. Now, ln T1 by 2, 1 upon T1 by 2, 2 all divided by ln A2 by A1 is equal to n minus 1. Where n, we know that order, therefore n is equal to 1 plus all this quantity. Ln T1 by 2, 1 upon T1 by 2, 2 all divided by ln A2 by A1. Okay. Therefore, half-life, if you know the half-life of a reaction at two different concentrations, if you know the half-life of a reaction at two different concentrations, you can calculate the order using this equation. This is the half-life at the concentration A1. This is the half-life at the concentration A2. This equation will help you to calculate the order. Now the fourth is isolation method. Fourth, isolation method. Isolation method. Students, in isolation method, this method is used to determine order of particular reactant. Order of particular reactant, not the overall order of the reactions. The all previous methods give you the overall order of the reaction, but here this will help you to determine order of a particular reactant. To determine order of a particular reactant. Okay. Take concentrations of all other reactants large excess. Take the concentrations of all other reactants large excess. Therefore, its orders become 0. Then find out order of that particular reactant. Okay. Suppose you have a reaction A plus B. A plus B gives product. You want to know what is the order of B. Therefore, take this is large excess, very large excess quantity, so that its order becomes 0. Therefore, rate is equal to K into B, and A raised to 0. A is 0, that 1. Therefore, rate depends upon only B. Then you can calculate the order of B with respect to differential rate expression or integral rate expression, or using half-life methods. Okay, this is the isolation method. I think this video is helping you. Thank you for watching.